integration by substitution, often called U sub, with indefinite integrals. Recall that the derivative of f of g of x equals f prime of g of x times g prime of x, which means that delta f of g of x equals f prime of g of x times g prime of x dx. So what we're doing very often with U sub or integration by substitution is finding an antiderivative of a chain rule. This is not always the case. This is usually how we start, and then we can extend this idea to other types of integrals that aren't exactly the end result of chain rules. But for now, we're going to think of it like that. So how does U sub or integration by substitution work? We will look at some examples, starting with the integral of the square root of x squared plus 1 times 2x dx. Notice that 2x is the derivative of x squared plus 1. What then if we let u equal x squared plus 1? I'm allowed to choose that. I can do any kind of substitution I want as long as the math is correct. And this gives us du dx equals 2x, a step I generally don't write anymore after the first example because I see that du is 2x dx. Which means we can rewrite this integral as what? Well, as a square root of u, because that's the square root of u, as we chose u. And then this entire piece back here, all of that 2x dx is exactly du. So what we've done is we've taken a complicated looking integrand and made it much simpler. Because this is a power rule. The integral of u to the 1/2 is u to the 3/2 divided by 3/2, but we will simply flip and multiply that, plus c. And then we could back substitute from u's into x's, where u was x squared plus 1. And we get our antiderivative. Next example. Let's find the integral of 2 cosine 2x dx. Notice that I have a function 2x. If it was just simply the cosine of x, I know how to do it. But the cosine of 2x gives us a little problem. But not if I let this equal u. So I'll put it over here. U will equal 2x. And then I know that du is 2 times dx. So I have both u and du exactly. That is 2 dx is exactly du. So I can do a substitution making this integral cosine of u du. Now we can find the antiderivative, which is the sine of u plus c, where u equals 2x. So a couple questions I get asked a lot. First of all, how do you recognize when to do a U sub? Well, in Calculus 1, that's a little bit of an easier answer. If you're finding an integral and you don't know how to do it, it's not one you have to have memorized, it's probably a U sub. A little bit more higher level thinking, I am looking for something along these lines. Do I have a function, really f prime at what I could call u, and then I can make this back part du. So if I can recognize that going on, I'm thinking it's a u sub. And there are other ones that I know by experience. So the next question might become, well, how do I know what to let u equal? Few things I key on. These are not mathematical facts, but just things I've seen after having done so many. If I have something inside parentheses, whether explicit or implied like this first one, or down here in cosine, those are implied parentheses, whatever is inside parentheses is very often the u. Another thing that I look for are problems like this. What if I have the integral of x over x squared plus 1? Well, I already pretty much see what my u is, because I see a u, right? And I want not only u, but its derivative, both of those things, to be part of my integrand. But if I didn't see it, here's the other thing I tell my students to look for. If I have a denominator, very often the denominator is your u. Well, now let's continue this problem. I do have u in the denominator, and I do have x dx, but I'm missing a 2. Is that a problem? Well, it's not. I can just multiply by 2. Does that change the expression? It does. So it's not correct unless I also multiply by 1/2. Because when I do this, I'm multiplying the entire expression by 1, so I don't change anything. So we will see that if we're off by a constant, a numeric multiple, we can just multiply on the inside and then by its reciprocal somewhere, I usually put on the outside. And we can do what we've been doing before. So now I have the integral of what? Well, the top is exactly du, and the bottom is exactly u, and then I have the times of 1/2 outside. We are now in a situation where we have an integral that we have to know how to do it, or else there's no other way to do it. We have to have the answer memorized. Where I know that the antiderivative of du over u is the natural log of u plus c. And now we can back substitute, put the natural log of, since x squared plus 1 is always positive, I don't really need the absolute values, so I'll get rid of them here, but you can leave them if you want to, and then plus c. Let's do another one where we're off by a little bit. What if we want to integrate x squared times x cubed plus 4 to the 5th dx? This is a u substitution. How do I know? Well, I have a function and most of its derivative here. So the function is generally u. It's also inside parentheses, so these things are lining up, the things I normally look for. We will let u equal x cubed. I could just let it equal x cubed, but why not let it equal x cubed plus 4? Because the derivative is the same either way. It's 3x squared, whether I put the plus 4 or not. So let's get rid of the plus 4 and put inside of our u. I have the u. I have most of my du. We're off by a factor of 3, so I'll multiply by 3. I have changed the expression, so I'll multiply by 1/3 on the outside. And now I'll rewrite it as 1/3 the integral of what? Well, u to the 5th, and then all of these parts become exactly du. Now we can integrate, so I have 1/3 times u to the 6th over 6 plus c. We'll simplify and back substitute, giving us 1/18 x cubed plus 4 to the 6th plus c. Let's keep going. What if we want to integrate e to the negative 2x dx? This is a u sub. How do I know? Well, experience, of course. Another way sometimes I think about this is I know how to integrate e to the u du. That's simply e to the u. So if I had e to the x dx, the integral is e to the x. What if I have something that looks more complicated? Not a big deal. Because if I know to integrate e to the u, it's telling me this part is the u. Side note, it's not the only way to do it, but it's a good way and it's the way I like to do it. So we'll let the power equal u. And then du is negative 2 dx. We're off by negative 2. I'll put it back here this time. And I'll fix the front by doing times negative 1/2. And now we have negative 1/2 the integral of e to the u du. Which of course is negative 1/2 e to the u, but I'll just go in and back substitute right away. Keep going. Even though this video might be a little bit longer, I think it's helpful to see a lot of examples. How about the integral of the sine of the square root of x over the square root of x dx? Now, it's not a basic integral, so for us in Calculus 1 it's a u sub. What should I let u equal? Well, I have a bit of a problem here. Maybe. Should I let the u equal the denominator or the thing inside parentheses? Well, they're both the same thing, so let's just let u equal the square root of x. And then du is 1 over 2 root x dx. So how do I substitute this in? Well, first of all, I need a 2 down here, really dividing by 2. So we need to multiply by 2 on the outside to kind of fix it. And then I have the sine of u. Now, should I put it over 2u? Well, no, because first of all, what would I do with the dx? But maybe more importantly, notice that dx over 2 root x is exactly du. So we can integrate the sine of u du, which is the negative cosine of u plus c. How about this one? The integral of the natural log of x over x dx. Side note, when we're doing a u sub, never do u equals x. It never helps you. The only thing it does is change all the letters. So how do I know what to let u equal? Well, u is going to be something, and sometimes it's easier to figure out maybe what du is, or at least look at these things in combination. So I kind of have two main choices. I could let u equals x. That's not a main choice. I could let u equal natural log of x, or I could give me du as 1 over x dx. I kind of gave it away. Or I could have let u equal 1 over x, and then du equals negative 1 over x squared dx. Now, when we choose u and or du, we have to have both of these things in my integrand. So do I have a 1 over x and a negative 1 over x squared, and basically nothing else, except for maybe a constant multiple? And the answer is, of course, no. But do I have natural log of x? That is, do I have u, and do I have du exactly inside here? Well, yeah, because that's u, and then dx over x is exactly du. So this becomes the integral of u du, which is u squared over 2 plus c, and back substituting, we get the natural log of x squared over 2 plus c. Let's look at a couple of disguised u sub ones. Let's do the integral of x over x plus 1 dx. I'm telling you this is a u sub. How do I know what to let u equal? Well, let's see. I'm looking for a function u and its derivative u prime, or we call it du. I don't really see that here. I could choose the thing inside parentheses. That's another thing I try to do. I don't have any explicit parentheses, but I do have a denominator. So let's let u equal the denominator and see what happens. Well, if u is x plus 1, then du is dx. And if I substitute in, we get x times du over u. Now this might seem like a problem because we need to have everything in terms of u's. So how do we handle the x? Very simply, since I chose u to equal x plus 1, then x must equal u minus 1. So if I rewrite this, we get u minus 1 over u du. You may think, well, that doesn't look any better, but it is much better because we cannot split up a denominator, but we can split up a numerator with a fraction, giving us 1 minus 1 over u du. Now, the integral of 1 with respect to u is u minus, and now we'll do the integral of 1 over u du is a natural log of u plus c. I'll call it c1. When I back substitute, we let u equal x plus 1. I did that intentionally. Is this a true statement? Why did I not put x plus 1? Could I have put an x plus 1? The answer is yes, I could have. Why did I not do that? Well, because c is a constant. 1 is a constant. So I just blended 1 into my c1 and called it c2. It's very typical when you look in the back of the book that the book answers will do something like that. So I wanted you to be aware that you might see something like that, or maybe on a multiple choice test. Let's do one final example. Another example of what I consider kind of a disguised u sub. How do I know this is u sub? Well, we're in Calculus 1. It's not a basic integral, so it must be u sub. What do I let u equal? Well, let's see. Do I see a function as derivative? Not explicitly. Let's try the denominator. Let u equal 1 plus x to the 4th. Then du is 4x cubed dx. We're off by a constant of 4. But we're also off by x's. It's okay to be off by a constant multiple, but it's not really that good if we're off by x's, generally speaking. Because I can't do times x squared and put 1 over x squared outside. That's not a true statement. Can't do that. So how do we handle an integral like this, knowing that it's u sub? Well, sometimes it's easier not to choose u, but to choose du. So I really have two choices for du. Either dx over 1 plus x to the 4th, and then we have to integrate that one. That's not looking promising. Or du is 2x dx. Well, at the very least, I can integrate this one, or I can say u must be x squared. We don't need to worry about the plus c. U is x squared. Does this help? I certainly hope so. We'll try it. So if I substitute in, the top is exactly du, and the bottom becomes 1 plus x squared squared, or u squared. And hopefully you recognize that we know how to do this integral. Because the integral of du over 1 plus u squared is the arctan of u, where u is x squared.